Hello and welcome back everyone. In this lecture, we are going to take a deep dive into the core building blocks of the Magic Wand application, the accelerometer handler, gesture predictor, and the output handler. Finally, we'll connect them together in the detecting gestures module, which integrates the entire system into one seamless loop. This is where the true project truly comes to life. Because without these components, the model is just a code sitting in memory. Let's start with the very first piece, the accelerometer handler. The accelerometer handler is responsible for capturing raw motion data from the device's built-in 3-axis accelerometer. In simple terms, it listens to the x, y, and z acceleration values as you move the board, and then it feeds this data into the model's input tensor for inference. But it's not just about reading numbers. It also has to make sure the data is usable. To do this, the handler uses a buffer. Instead of sending every single reading to the model immediately, it collects 128 sets of values, that's 128 readings for each axis, for a total of 384 numbers. Only after the buffer is filled does the system run inference. Why this is important? Because gestures are not instantaneous. They happen over a short duration, maybe 1 or 2 seconds. And the model needs a complete sequence of motion to recognize a pattern. Without buffering, we would be trying to classify incomplete gestures, which would confuse the model and lead to poor accuracy. Another key detail is device-specific implementation. For example, on the Arduino Nano 33 BLE Sense, the accelerometer runs at about 119 Hz, which means it gives us 119 samples per second. However, our model expects data at 25 Hz. This mismatch could cause problems because the model was trained on slower data. To solve this, the handler performs downsampling, where it deliberately drops extra samples to bring the data rate down to 25 Hz. This ensures consistency between training and real-time use. The handler also has a reset mechanism. After a gesture is successfully detected, the buffer is cleared to make room for new input. This prevents overlap between old data and new gestures, which could otherwise confuse the system. So, in summary, the accelerometer handler is the data provider. It captures motion, organizes it into windows, adjusts the sampling rate, and hands it off to the model in a clean and structured way. Once the model processes the input and produces its output probabilities, the next question is, how do we decide whether a real gesture was made? That's the job of the gesture predictor. At first glance, it might seem simple, just take the class with the highest probability. But in practice, things aren't so clean. Random noise or accidental hand movements might produce occasional spikes in probability, leading to false positives. Imagine your wand activating every time you scratched your head, which is not very magical. To prevent this, the gesture predictor uses two strategies. Probability thresholds. A prediction is only considered valid if its probability is greater than 0.8, meaning the model is at least 80% confident. Anything below that is ignored. Consecutive confirmations. Even if a gesture passes the threshold once, it won't be immediately accepted. The predictor requires the gesture to appear consistently across multiple interferences. For example, on the SparkFun Edge board, the wing gesture needs to be detected 15 times in a row, ring 12 times, and slope about 10 times before the system confirms it. This combination of thresholding and repetition dramatically reduces false detections, making the system far more reliable. And here's an interesting point. These parameters can be tuned for different boards. Faster devices can handle more inferences per second, so they can require higher confirmation counts. Slower boards may lower the requirements to keep the system responsive. The gesture predictor, in essence, is the gatekeeper of the application. It ensures that only gestures which are both confident and consistent make it through. Now, once a gesture is confirmed, we want to let the user know. That's where the output handler comes in. This is the final stage of the system, and its job is to provide immediate and understandable feedback. On the Arduino Nano 33 BLE sense, the simplest form of output is the LED indicator. For example, when the model detects a wing gesture, the LED lights up to show recognition. But we also have the option of serial output. This means the device can send text to computer serial monitor displaying messages like wind detected or slope detected. This is extremely useful for debugging, monitoring, and extending the project. The output handler is deliberately simple, but then that's its power. It closes the loop between the recognition and interaction, and just like with the other components, it's flexible. Instead of controlling LEDs, you could program it to activate a motor, send data over Bluetooth, or even trigger a smart home device. In other words, the wand is just the beginning. The same framework can be adapted to countless other use cases. Now that we have gone through each piece individually, let's put all of them together in the detecting gestures module. This is the central loop of the Magic Wand application. Here's how it works step by step. The system starts by reading raw acceleration data and sorting it in the input buffer. Once the buffer is full, the TensorFlow Lite interpreter runs interference on this window of the data. The gesture predictor just checks the model's output and applies thresholds and confirmation rules. If a gesture is confirmed, the output handler takes over and the lights or the LEDs are lit up or it prints a message. The accelerometer buffer is then reset so the system is ready for the next gesture. This cycle repeats continuously many times per second. It integrates all the pieces we discussed: sensor capture, inference, prediction, and output into one seamless responsive system. On the Arduino, all of this is managed inside two functions: setup and loop. The setup function runs once at the beginning. It initializes the TensorFlow Lite interpreter, allocates memory, and configures the accelerometer. The loop function is then executed repeatedly, capturing data, running the inference, and handling output. This is the heart of the application. Because the model is small and efficient, the wand can run multiple inferences per second, making the gesture recognition smooth and real time. So to wrap up everything that we have learned till now, the accelerometer handler ensures that data is captured correctly, buffered, and downsampled. Then comes the gesture predictor, which acts as a filter, confirming only confident and consistent values. Then the output handler provides immediate feedback, making the recognition visible and interactive. And finally, the detecting gestures module that ties it all together into a continuous, always-on pipeline. This design is what makes the Magic Wand project not just a demo, but a reliable framework for real-world gesture recognition on microcontrollers. So, in the next session, we'll move forward and talk about how we can deploy the system onto microcontrollers and how techniques like quantization and optimization make it fast and power efficient. So see you all in the next video. Thanks. Bye.